Welcome back. In topic 1 to 4, we focused on the engineering application part of radiation heat transfer. In topic 5, we will focus on radiation heat transfer theory, property, and network. A. Radiation heat flux. First, we introduce irradiation G to represent the total radiation heat flux incident on a surface. Second, when a radiation heat flux strikes the surface, some is reflected, some is absorbed by the medium, some is transmitted. This kind of medium is called transparent medium, like glass. Otherwise, when the radiation heat flux strikes the surface, if there's no transmission, this kind of medium is called opaque medium, like wood. Third, we introduce radiation properties, absorptivity alpha, reflectivity rho, transmissivity tau, to represent a fraction of irradiation G absorbed, reflected, and transmitted, respectively. Therefore, equation 1 is for any medium, but equation 2 is for opaque medium only. B. Emitted radiation heat flux. First, all matters have the ability to emit radiation heat flux as long as its temperature is above 0 Kelvin, besides its ability to reflect or absorb the radiation heat flux. The emitted radiation heat flux, E, can be calculated from equation 1. Furthermore, if the surface is a blackbody surface, it emits the maximum radiation flux. Therefore, it is labeled with EB. Finally, for any surface emissivity, epsilon can be defined as the ratio between these two fluxes. Second, we introduce radiosity J to represent the total radiation heat flux leaving the surface. By definition, the radiosity J is a combined reflect radiation heat flux and emitted radiation heat flux. Third, we revisit blackbody surface to check its two implications. By comparison with gray surface, the blackbody surface first has emissivity over 1, therefore it emits the maximum radiation heat flux. The second, the blackbody surface has absorptivity of 1, therefore there is no reflection. As a result, the radiosity and the maximum emitted radiation flux are the same. C. Net radiation heat rate equation and network. We have discussed there are two kinds of net radiation heat rates. One is QIG between surface I and surface J. The other is QI from a single surface I. First, the heat rate equation for Qij is represented in equation 1, which is the radiosity difference between surface I and surface J over the geometric resistance Rij, which is 1 over surface area Ai times mu factor Fij. The heat rate equation for Qi is represented in equation 2, which is Ebi minus Ji divided by surface resistance R epsilon I, which is 1 minus emissivity over emissivity times the surface area Ai. Second, if we borrow the concept of thermal circuit and apply it to our radiation heat transfer, we have our radiation network. Here is how you draw the radiation network. For Qij network, you start with radiosity Ji over surface I, then going through geometric resistance Rij, reaching radiosity Jj over surface J. Next, label arrow and a symbol Q to represent flow direction and heat rate. Similarly, for Qi network, you start with Ebi, then going through surface resistance and reaching Ji. Next, label arrow and a Q to represent flow direction and heat rate. The difference between these two is that we use the empty dot to represent the temperature in thermal circuit, but we use empty dot to represent radiation heat flux in radiation network. D. Have these two net radiation heat rates related? First, in an N-surface enclosure, the energy conservation requires that net radiation heat rate from a single surface I, Qi, is due to the net radiation heat exchange with all other surfaces within the enclosure. Second, equation 2 is equation 1 with Qi replaced by the definition, with Qij replaced by the definition. Third, let's apply equation 1 and 2 to this example of 3 surface enclosure. The total number of radiation surface is 3. We let I equal 1. So we're interested in the Q1 on surface 1. Then equation 1 becomes Q1 equal Q12 plus Q13 with Q11 to be 0. E. Radiation roadmap. The reason we come back to the radiation roadmap is to confirm that we have covered all the equations in the roadmap so that you feel comfortable and confident to apply those equations. Next, we will discuss the radiation network for different enclosures. F. Radiation network for two gray surface enclosure. First, this is a two gray surface enclosure system. We have radiation heat flow from surface 1 to surface 2 due to the temperature difference. Second, this is radiation network for two gray surface enclosure. Here is how you draw the radiation network. You start with EB1, going through surface 1 resistance, reaching J1, and then going through geometric resistance, reaching J2, then going through surface 2 resistance, reaching EB2. Next, label arrows and Q to represent flow direction and heat rate. Please note, one assumption made is for heat flow Q from EB to J, it is a positive sign. Third, by checking the radiation network, we have noticed these three resistance in series. Therefore, the radiation heat rate can be calculated using equation 1, which is EB1 minus EB2 divided by the summation of these three resistance. G. Radiation network for three gray surface enclosure with radiating surface. First, radiating surface represents an insulated wall on one side, and on the other side it absorbs all radiation heat and then radiates all away. Therefore, there is no net heat flow in or out through this insulated wall. Second, this is the radiation network for three gray surface enclosure. Here is how you draw it. You start from EB1 to EB2. EB1 resistance, J1 resistance, J2 resistance, EB2. Then from EB2 to EB3, EB1 resistance, J1 resistance, J3 resistance, EB3. Then from EB3 to EB2, EB3 resistance, J3 resistance, J2 resistance, EB2. Next, label arrow and symbol Q to represent flow direction and heat rate. For three gray surface enclosure with radiation surface, since there's no heat flow, as a result, this path is broken. Now it becomes the network for the enclosure with radiating surface A3. Third, by checking the network, we have noticed these two resistance are in series, combined is in parallel with this resistance, then combined is in series with this resistance and this resistance. As a result, the radiation heat rate from surface 1 to surface 2 can be calculated from equation 1, which is EB1 minus EB2 divided by the total radiation resistance between them. H. Radiation network for blackbody surface enclosure. First, let's revisit black surface for its two implications. The first implication is that J is the same as EB. Therefore, in all the equations, J will be replaced by EB. The second implication is the surface resistance R epsilon is 0. Therefore, the network for QI becomes a straight line. Second, the QIG is calculated in equation 1. For example, if we're interested in the heat flow from surface 1 to surface 3, Q13, we simply replace I with 1, J with 3 to get equation 2 for Q13. Third, QI is calculated in equation 3. For example, if we're interested in the heat rate from single surface A1, we let I equal 1, and the total number of the radiation surface is 3. We plug into equation 3 to get equation 4 for QI. Fourth, this is radiation network for 3 blackbody surface enclosure. Let's make a comparison between network for gray surface enclosure and the one network for black surface enclosure. The difference between these two is that the J is replaced by EB. The network for Q 1, 2, 3 is replaced by straight line. Here is how you draw the radiation network for 3 black surface enclosure. You start with EB1 resistance, go to EB2, then EB1 resistor, going to EB3, then EB3 going resistor going to EB2. Next, label arrow and Q to represent flow direction and heat rate. I. Radiation heat transfer is a complicated process. It is. The complexity is in that the radiation property like emissivity, absorptivity, and reflectivity all depend upon temperature of the medium, the flow direction, and the radiation wavelengths. As a result, the radiation heat flux is determined from the knowledge of directional and spectral nature of radiation. This will leave for your future study. Let's have fun with radiation property quiz. We have 4 mediums with different color and texture. The first quiz question is, which one is the best surface to reflect radiation? The answer would be A, shining white. The second question is, which one is the best surface to absorb radiation heat? The answer would be the black. That's the reason during the summertime you wear the light color clothes. At this point, we covered topic of 5. It's really heavy on variables and the math definition. We discussed radiation heat flux and the property, radiation heat equations, and on how to draw radiation network. The goal is for you to understand radiation heat transfer better. Now we completed chapter 13 and 12. Here is the beautiful summary and outcomes on concept, variables, scales, and equations. At this point, we end chapter 13 and 12.